job on me. This is called Arrhenius' equation, and this is the equation that we're going to use to calculate the activation energy or the rate constant where we already know the activation energy. So there's a lot of things that we can do with this. So let's take a look at a situation that is described in this problem right here. This example, in a reaction, the rate constant for a reaction at 327 degrees Celsius is 2.7 times 10 to the negative 4 moles per liter, negative 1 second, negative 1. Now this is telling us the second order reaction. This is some of the exponents out to negative 2. We never really dealt with that except for one time, and it's really not important in this problem. It doesn't make a difference what order the reaction is, it's still going to do the same. So no worries about that. And the same reaction run at a different temperature, a higher temperature, we know it's going to go faster. Well, the rate constant for that is 3.5 times 10 to the negative 3. Well, it was 0.00027, and now it became 0.0035. So it's more than 10 times faster. And what is the activation energy? So we want to know what is the activation energy that causes this change to be 10 times faster than what it was before. So here's how we do it. So we got the first temperature we said is 327 degrees Celsius. We're going to add 273 because we have to change that to Kelvin. That's 600 K. Don't put a degree symbol for Kelvin, it's just K. The second temperature was 377 degrees Celsius. Add 273 to that. This is 650 K. The K1 associated with this is given to us as 2.7 times 10 to the negative 4. I'm not going to worry about the label. It's totally inconsequential to this problem. And K2 here is 3.5 times 10 to the negative 3. Now I'm going to suspect in a 50-degree change like this, we got more than 10 times, so I'm going to suspect that this is going to be pretty high activation energy. All right, so we write down the formula, natural log of K1 over K2 equals EA over R times, now notice here, this goes in order 1, 2. This is why I was able to catch my mistake so quickly, because when you come over here, the numbers in order switch. So it's the second temperature minus the first temperature. T2 minus T1. Okay, so this will be the natural log of K1 is 2.7 times 10 to the negative 4 over K2 3.5 times 10 to the negative 3 equals EA, which we don't know. R we know is 8.31 joules per mole Kelvin. But since we got logarithms all over the place, I'm not going to worry about labels for this. Normally I would, but I'm not for this because I know activation energy is going to turn out to be joules per mole like we saw in those diagrams. Second temperature, this should be to the negative 1 power. This should be the negative 1 power. So this is going to be second temperature 650 to the negative 1 minus 600 to the negative 1. Now, I've done the mathematics for this in the problem here. So, the left-hand side was equal to negative 2.562. I went 4 sig figs. A lot of times there'll be really small differences, and if you don't account for that, sometimes the answers go way off. The right-hand side was equal to 1.54 times 10 to the negative 5 times EA. So I'm going to divide this by that, and I get 1.66 times 10 to the 5th joules, or 166,000 joules per mole. That is a substantially large activation energy. Okay? The next one, we're going to do the same reaction, but now we're going to take it up to 427. So we've increased another 50 degrees. We should suspect that it's going to multiply the rate, or the constant, by 10 or more than 10, 11 or 12, whatever it was. So let's see. Okay, so, and what I'm going to do is I'm going to take the very first T1 we have here, the 327 and K1, 3.7 times 10 to the negative 4, and use it again. So we got T1 is 327, which we said was 600K, and we said that K1 is 2.7 times 10 to the negative 4. Again, I'm not worried about the label. Now my T2, instead of being able to use the other problem, I'm going to use the 427 degrees Celsius and add 273 to that, and that's going to make that 700 Kelvin. Well, the fact that I've increased the temperature knows that my rate constant is going to go up. And then I'm going to make K2 then my unknown. Now I do know that my activation energy is going to stay the same. Remember I showed you the diagrams how constant that loop is? That does not change at all. No matter what the temperature, it is going to be that value. So that's going to be 1.66 times 10 to the 5th joules per mole. Again, not going to worry about the label of all these logarithms flying around. But then I'm going to go back to Arrhenius' equation, natural log K1 over K2 equals EA over R times T2 to the negative 1 minus T1. I actually remember my expenses. Aren't I a good boy? All right, so natural log K1 we said is 2.7 times 10 to the negative 4 over K2. We don't know what that is. That's what we're going to solve for. So we've got all kinds of manipulations with this Ln, as you see. The activation energy we calculated to be 1.66 times 10, not negative 5, that's positive 5. It's a really big number, not a really small number. Divided by 8.31 joules per mole Kelvin times, and second temperature now is 700, negative 1 minus the first temperature, 600, negative 1. Okay, so that's our setup for this. And again, I've done the math in the problem. Oops, go down to the results. That's the previous result. That would be equals. And so when this is the equation I just wrote down here with that stuff thrown in. And it turns out the right-hand side of the equation is negative 4.756. So all of this right here is negative 4.756. And that leaves us this. Now, this is actually has a natural log, kind of got chopped off or removed from the previous line. So there's a natural log in front of this. You need to get rid of the natural log. So that means we're going to have E caret for this and E caret for this. So that's why I have E caret to both sides of the equation. And you get 2.7 times 10 to the negative 4 over K, and that should be K2. I'll get that fixed for your script. Equals, and then this value right here is 8.60 times 10 to the negative third. So in mathematics, when you have a formula with a variable in the denominator, you just simply switch these two around. So 8.60 times 10 to the negative third goes on the bottom, K comes out here, and you end up with 3.14 times 10 to the negative 2, and the label is M negative 1S negative 2, or negative 1. So, that's how you do those problems. Your practice problems, 63 through 66. I do want to caution you on the last two. They don't give you numbers of a quantity. They say instead it's like tripled and quadrupled. So I would suggest you just pick a number like 1 and 3 or 1 and 4 for those numbers. That's one's being tripled, the other's being quadrupled. Don't make life complicated and don't get upset by it. They're actually making the problem pretty easy for you. So have fun with that. Good luck.